Hello everyone. We are going to look at factoring special products this week. So you can put your name on that first slide. Last week we focused on factoring the GCF out and also factoring when the A value is equal to 1. We're going to look at two special patterns that come up in factoring in this week's lesson. So push ahead to slide 2. What we're going to see a lot in this lesson are perfect squares. So this is when you take the product of a rational number and multiply it by itself. So for the first one, for 1, to get it squared, we're doing 1 times 1, which equals 1. Perfect. The second one, 2 times 2 is 4. 3 times 3 is 9, and we're just filling this chart in. 4 times 4 is 16. 5 times 5 gets us 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. And 10 times 10 is 100. So that's our first column. Those are our first 10 perfect squares. 11 times 11 is 121. 12 times 12 is 144. 13 squared is 169. 14 squared, or 14 times 14, is 196. 15 squared gets us 225. 16 squared is 256. 17 squared is 289. 18 squared, 324. 19 squared is 361. And finally, 20 squared is 400. So these lists, these numbers, are our perfect squares. So we're going to see them in some polynomials, and we're going to want to be able to identify that they are a perfect square and then know how to take the square root of them. So I just want you to make this list, have this handy as we're working throughout this lesson. Push ahead to slide 3. So the first pattern we look at is the difference of perfect squares. So the key part that we have is this word difference, which means we're always going to have subtraction in the middle. We'll have some A term squared minus some B term squared. And the way that we factor it is A plus B times A minus B. So A plus B and A minus B are what we call a conjugate pair, meaning they're the same terms, only one is addition and one is subtraction. When you multiply these conjugates, you'll get the difference of perfect squares. So some examples of some conjugates. If we have x plus 3, the conjugate would just be x minus 3. If we have x minus 16, the conjugate would be x plus 16. If we have y plus 4, the conjugate is y minus 4. And if we have x minus 2, the conjugate is x plus 2. So just getting used to how we write these conjugates, and we'll see how this difference of squares works when we're factoring. So when you have this all set, push ahead to slide 4. So we're going to do some discovery. So let's multiply and see what happens. Remember, we have two methods for multiplying. We have our box method. So you can make a box if you want to use that method. And we're multiplying x and positive 6 with x minus 6. Now x times x gets us x squared. X times negative 6 is a negative 6x. X times positive 6 is a positive 6x. And then 6 times negative 6 is a negative 36. So notice that this 6x and negative 6x are going to cancel each other out. So we're just left with x squared minus 36. X squared is a perfect square because it's x times x, and 36 is a perfect square because it's 6 times 6. So that's why it's factored as x plus 6 and x minus 6. So let's look at another one for y plus 10 times y minus 10. I'll do the FOIL method for this one. So first we have y times y, which gets us y squared. Y times negative 10 gets us a negative 10y. 10 times y is a positive 10y. And 10 times negative 10 is a negative 100. Now again, this negative 10y plus 10y are going to cancel out to 0. So we're just left with y squared minus 100. Y squared is a perfect square because it's y times y. And 100 is a perfect square because it's 10 times 10. So this is the polynomial version, and this is our factored version. Y plus 10 times y minus 10. So let's try and do some factor practice on the next few slides here. So here's our pattern. A plus b times a minus b equals a squared minus b squared. So if we're going backwards, this is our a squared, and this is our b squared. And they're being subtracted, so we know it is the difference of perfect squares. Now, the way that I like to think about this is the square root of x squared is just x, because x times x is x squared. And the square root of 64 is 8, because 8 times 8 gets us 64. So there's our a and our b. So when we put this in factored form, we're just going to have x plus 8 times x minus 8. Perfect. Over on the right, we have that 81, and we also have that x squared. So again, the square root of x squared is just x. The square root of 81 is 9. So we're going to do x plus 9 times x minus 9, getting that conjugate pair. And that is our factored form. Beautiful. This is the difference of perfect squares. When we have two terms, they're being subtracted, and they're both perfect squares. Let's go to slide 6. 9x squared minus 16. So the square root of 9x squared. The square root of 9 is 3. The square root of x squared is x, right? 3x times 3x gets us 9x squared. The square root of 16 is 4. So here's our a and our b, so now we can just plug it in. So we have 3x plus 4 times 3x minus 4. Perfect. We're on the right. We have 25x squared. So the square root of 25x squared is 5x. 5x times 5x is 25x squared. The square root of 49 is 7. 7 times 7 gets us 49. So we take those terms and we write it as a conjugate pair. So we have 5x plus 7 times 5x minus 7. Beautiful. Push ahead to slide 7. 100x squared minus 9y squared. So we have subtraction, so that's good. And 100x squared is a perfect square. The square root of 100 is 10. Square root of x squared is x. Square root of 9y squared. Square root of 9 is 3. Square root of y squared is y. So as a conjugate pair, we have 10x plus 3y times 10x minus, ooh, my pen, 3y. On the right, we have 64y squared. So the square root of 64y squared is going to get us our a value. The square root of 64 is 8, and the square root of y squared is just y. Square root of 4x squared will get us 2x. Make your conjugate pair for your factored form. We have 8x plus 2y times 8x minus 2y. Perfect. Push ahead to slide 8 when you're ready. So now if we start with our factors, we can write it as our difference of perfect squares. So notice we have a conjugate, same terms, one is plus, one is minus. So if we square them, because we're working backwards now, 2x squared, or 2x times 2x, is 4x squared. 5 squared is 25. So we can write this as 4x squared minus 25. And that's our polynomial form. On the right, we have an x. X squared is just x squared. And 3 squared, 3 times 3 is 9. So this factored form is x squared minus 9. Perfect. Slide 9 when you're ready. We're going to do this again, putting it into our polynomial form. So we have x plus 4 times x minus 4. So our x squared is x squared, and 4 squared is 16. So this can just be multiplied as x squared minus 16. So we don't have to do the whole box method or FOIL method. We can just use that pattern. When we see the conjugate pair, we know it's going to be multiplied out to this. On the right, we have a 3x, and we're going to square that. 3 squared is 9, and then we have an x squared. And our second term is a 4y squared. 4 squared is 16, and then we have a y squared. So this is just going to be simplified to 9x squared minus 16y squared. Perfect. That is the difference of perfect squares. So that's our first big pattern that we're looking at this week. And we're going to look at the second big pattern next on slide 10. Still has to do with perfect squares. So these are called perfect square trinomials. So our first term is a perfect square, square of the first term of a binomial. Our last term is also a perfect square. And in the middle, we have twice the product of the binomial's first and last term. So we start with something like a plus b squared, and it multiplies out to a squared plus 2ab plus b squared. Here's another visual, a squared twice a times b plus b squared. This one, the difference here is if we have a subtraction sign in the front of our trinomial here, then it's just going to be a minus b squared. I'm going to pause the video here, and we're going to look into the practice together in part 2. So come back and check out part 2, and we'll finish out this slideshow starting on slide 11. You got this, y'all.